So I'm going to talk about a prototype that's a very, very personal project to myself that it's called Worldwide Telescope. And this started about 4 years ago. My brilliant developer, Jonathan Fay, and myself were sort of really interested in creating a really rich learning environment. Before I get too far into that, I just wanted to say something about the 5 words. When I saw sort of the 5 words there, they really resonated with me. In fact, I have my own sort of 5 words. Actually, there are 6. Sixth one is prototype and iterate. And this Project Worldwide Telescope that we've been building is actually a prototype. We've been out for a couple of years, but we're in probably several hundred iterations or versions of this prototype, and now it's truly gone global. But my favorite word amongst all of these is imagine, which is really where the origin of the project was. When I was a kid, quite a long time ago, I had this little book that I got. It's a little golden book, and actually you can tell how old it is because it says 150 paintings in color, right? Color was new then. And I remember drawing sort of pictures of Jupiter in crayons, and I really wanted to sort of see the Milky Way and the things that were in the book. But of course, I grew up in Los Angeles, and you know, between the smog and the city lights, there was really nothing that I could see, and it was a bit frustrating. And what I really wanted is sort of this. I wanted to be able to go out into a night sky and to be able to really see as if I had like the biggest telescope in the world. And on top of that, I also wanted to have like a Harvard astronomer to be there to sort of explain, what am I looking at? You know, what's going on there? Because I think being able to see a night sky, you know, you start to get familiar with it. You get associated with, you know, you learn about, well, if I see this, that means it's this time of year or what time it is. And this is the thing that connects all of us. And the fact that we're missing this, I think, is really somewhat of a tragedy. And so I've been thinking about this project for a long time. And what I wanted to build was this thing called the Worldwide Telescope. And the Worldwide Telescope is a very, very rich 3D learning environment. And what you're looking at now is the Worldwide Telescope. In fact, this whole presentation is in Worldwide Telescope. And you're looking at the night sky, and as you start to see a little bit of a glow there on the left, you're looking at the largest digital image ever assembled. This is from thousands of pictures from the Palomar telescope stitched into one giant image, which is 1 trillion pixels. So if you're looking here at the center of the Milky Way, there's actually a supermassive black hole in the middle of the Milky Way that's about 4.5 million times the mass of the sun. If you look down there, you see a little thing that looks like North America. Just below that, there's a supernova remnant. I mean, these are the kind of things that you can see. So when you have the entire sky there to look at, you can, because it's such a large image, you can decide, well, what's that fuzzy patch there? I want to be able to go in and look at that and seamlessly sort of see what's going on with that. That happens to be our nearest galactic neighbor. And in fact, all the sprinkling of stars that you're seeing around it, those are stars that are in our galaxy. The stars in that galaxy are so far away it looks like fog. But let's go up to some place that's a little bit more familiar, like you can recognize the Big Dipper there. Do you know if you look above the bowl of the Big Dipper, there's actually 2 fuzzy dots, and those are actually 2 galaxies that are actually colliding and interacting. And what I'd like to do is I'd like to have an astronomer sort of tell me what's going on with that particular galaxy. So this is called M81 and M82. But she's essentially talking about this particular galaxy, but if you could hear it, essentially it's kind of like video. There's narration going on, there's music in the background, but at any point I can sort of pause this, and it's not like a video where if you pause there's not much else you can do. you're actually in the environment for a worldwide telescope. So you're looking at this particular galaxy, but you can see what that galaxy looks like from any other telescope, okay? You're getting the context of where it is in the sky. And as I zoom in and zoom out within the context of the sky, you can sort of see in the lower right-hand corner the field of view that we're looking at. If I was really interested in this particular galaxy, there are other guided tours, if you will, that mention the different galaxies. So I could branch off from one story into another story, perhaps deeper about this particular galaxy. We're checking the audio. Oh, that one, okay. Let's see if we can.
This Spitzer Space Telescope image uses long wavelength cameras that can see
works.
heat, just like the one that took
Okay.
Galaxies are filled with tiny particles.
So let's jump ahead to this. Okay, so what we've built here is we built a really, really rich visual 3D environment that has the capability of telling stories within this, where you can add narration, you can add music, you can add graphics, you can add animation, you can add links to other sources on the internet. Because when you're trying to teach somebody something really new and that they're not familiar with it, I think you really have to start with a story. And that's what teachers are great at. Putting a question out there, creating something that gets them interested in something. But then beyond that, this is how we learn in the real world. Once your interest has been piqued, you want to give them the ability to develop mental models. And that's how we learn in the real world. We end up, through interaction, understanding the spatial context of something. And then once you start developing this model through interaction, you want to then connect it to other information so that model starts to get refined and validated. So I have this sort of contextual narrative, which is an architecture, and that's the underlying architecture of what we built within Worldwide Telescope. So what I'm going to do next is I'm going to show you what a 6-year-old has done with Worldwide Telescope.
Hi, my name is Benjamin. I am 6 years old and I live here. Actually, I live over here in a big city called Toronto. On clear nights when I look up in the sky, I see something like this. The tour I want to take you on is of the Ring Nebula, which Wikipedia, the Free Encyclopedia, also calls M57. I don't know what that means really, but I think it's like a jewel in the sky. The Ring Nebula is in the constellation of Lyra. Lyra is also where the brightest star in the sky is. This star is called Vega. The Ring Nebula is a little ways away from Vega over here. My dad says that he doesn't think the Ring Nebula is too far away. I read that it's 2,300 light years away, which seems like a very long bike ride. This is not how I see the Ring Nebula. I see it like this. The Ring Nebula was discovered a long time ago by someone in France. This picture of the nebula is beautiful. It looks like a precious blue gem in the middle of some red orangey stuff that looks like fire. I read that's because different gases give off different colors. You can see green, yellow, red, and blue. A nebula is what happens when a star like our sun dies. It lets out its remaining energy and expands, making lots of pretty pieces that one day can become planets. I think it's neat that stars can be so amazing for so long. I wonder what Vega will look like when it dies. That's my tour. I hope you liked it as much as I liked making it.
So he's a precocious kid. So I'm showing you essentially what this presentation is. Essentially, it's a number of slides. The numbers down below are how long that slide is up for, and essentially the authoring environment to do these is built into Worldwide Telescope. So I'm going to show you another tour, and we'll sort of take it to the next step here. I'm just going to bring this thing. So some folks at Harvard were really interested in Worldwide Telescope and how it might be used, can be used in the classroom. And so this is a tour that a teacher built to teach kids about understanding the phases of the moon. And they did this with about 150 kids.
Understanding the moon's phases, a tutorial. You've likely been outside at various times of night and day and observed that the moon looks different on different days. It's a common misconception that the moon is only up at night, and many people are surprised to realize that you can sometimes see the moon during the day. The times that the moon rises and sets changes with the moon's phases, so the moon is frequently visible during the day. It usually just gets lost in the glare of the much brighter sun. What causes the moon's phases? In other words, why does the moon look different on different days of the month? Discuss your ideas with your partner or group.
So I'm going to jump ahead a little bit.
The moon orbits the Earth as the Earth orbits the sun. The configuration of the Earth, sun, and moon on any given day determines the phase of the moon we see on Earth. In this diagram, we're looking down on Earth from above the North Pole. And note that this diagram is not to scale. This means that objects in the diagram might not have the correct relative proportions. The moon is a sphere shaped like a ball, and the sun only lights up half the moon at any given time. During new moon, when the moon appears dark to observers from Earth, the moon is between the Earth and the sun. This is what things look like from overhead. Remember that this diagram is not drawn to scale. Let's see what this looks like from the side. The sun is lighting up the side of the moon that faces away from Earth. A viewer from Earth sees a dark or new moon. Let's pan around. This is what the side facing the sun looks like.
So I'm going to continue to jump ahead
first
here.
Comes from the fact way through the sun's rays are shining. Half of the lit moon. The sun's rays are shining from the right, lighting up the right half. Half of the lit side and half of the dark side are facing Earth. This half and half view is called a first quarter moon. The sequence that follows shows the moon completing a full cycle from new moon to full moon and back as it completes an orbit around the Earth over the course of almost 1 month. We start at new moon. We go to a waxing crescent moon. Waxing means that we're seeing more and more of the lit side of the moon. First quarter. Waxing gibbous, full moon. Now we're at waning gibbous, and waning means that we're seeing less and less of the lit side of the moon. Third quarter, waning crescent, and back to new moon. Now it's time to check your understanding. In the diagram below, the moon is shown at 4 possible positions relative to the Earth and Sun. Click on the image that shows where the moon is when an observer in the northern hemisphere sees the moon looking like the image to the right.
So how many people think that the answer is A?
Down on the Earth from above the North Pole, and this
How many people think the
not
answer is
scale.
B? Few? Not too many. How many people think the answer is C? A few more. Nobody's afraid to try. How many think the answer is D? Oh. Okay. Well, the answer is actually C.
Right. When the moon is in this position, sunlight is shining from the right side.
So I'm going to jump ahead.
Let's try another one.
Okay, we're going to skip that.
Right.
And then at the very end, I've inserted actually some slides. So this is the sort of the result after the study where they polled kids in terms of what they thought. Some of the comments were actually kind of fun. Awesome, amazing, cool, incredible, repeat 30 times. My favorite one is that it gave me a better mental model of the universe, which has really sort of been my goal of this thing. So the study group had about 150 students divided into 2 groups. And the first question was about memorizing, and both groups sort of did the same in terms of results, in terms of the memorization. But what's interesting is when they were evaluating how really understanding in terms of what that phase of the moon meant, And if you look at Worldwide Telescope, those that used it were about sort of twice as likely to get the answer right. And those that actually, in terms of getting it wrong, they did better. The fewer students got it wrong. And these are kind of interesting, too, in terms of the level of interest in astronomy. The group without Worldwide Telescope actually started with a higher level of interest in astronomy, but ended up a bit lower versus compared to those that did. And what's kind of interesting here, too, if you look at the how interested are you in using a real telescope? There were actually more people interested in the other group, but their interest went way down. And those that used Worldwide Telescope, it was statistically very, very significant in terms of the difference there. So I'm going to show you one last capability, and there are many, many things to show you here. But this is around some newer capability of using Worldwide Telescope to illustrate how we can integrate data into this environment. Oops, sorry, clicked on the wrong thing here. So what I didn't show you behind it is in any of those objects we look at in the sky, you can then dig behind it and click and get access to Wikipedia for that object and information sources from all over the web. So this is where we brought in earthquake data for about a year and a half. It's basically about 50,000 earthquakes. And these are represented on the Earth from USGS, and you'll be able to sort of see what that looks like here. So this is just, again, a tour that we created. You can sort of see the slides as it moves from one point to another. And so this area above New Zealand actually has some of the deepest earthquakes on the planet. In fact, if you start looking at these pattern of earthquakes, the lighter blue is shallower water, and you're seeing the Pacific plate go underneath the continental plate. And you can see the earthquakes that are happening at the boundaries of those subduction zones, which become very, very obvious. Follow it down towards California. We just passed where we are. You can see the San Andreas. You can look down here, Central America, again, another subduction zone. You can see the pattern of earthquakes down below the subduction zone. If we go into the Caribbean, you can see the Haiti earthquake right there on the surface. This is an area above Puerto Rico, which is extremely active in terms of earthquakes. So we can compress time where you're looking at a pattern of earthquakes, a year and a half of earthquakes in about 15 seconds. So you're starting to see spatial and large-scale temporal patterns, which is something you really can't do particularly well in sort of any other application. But within Worldwide Telescope, you have the ability to sort of go in and look at any of this data. In here, I've sort of suppressed, but we could hover over any of these things and go directly in to find out exactly what the magnitude and depth of any of that data is. So I've sort of run out of time here, but I wanted to finish off just sort of showing we've gone from the Earth, we're going out into the solar system. And here in the solar system, what you're looking at is these yellow things are objects. We've accelerated time, and these are all the 500,000 near-Earth objects, which are basically about the size of a school bus or larger. And you can see the asteroids forming in a cloud here. This yellow ring here is actually the planet Jupiter. And most of us probably didn't know that Jupiter has these little gravity wells on both sides called Lagrange points, which is where all these asteroids are clusters on both sides of this. And I actually never knew that until I actually saw, this is real data, plotted here in terms of where things are in Worldwide Telescope. But if we sort of move away from the solar system and start to move out, we can see the local stars that are nearby. We can exit the Milky Way. This is the latest view of what the Milky Way actually looks like, which is a bar galaxy. And we're going into the rendering of the large-scale structure of the universe. These are 1 million galaxies, okay? And what's interesting about this rendering is that it's actually the most accurate rendering of the universe that's been done so far. And I'm actually going to exit out of this tour and sort of take you a little bit and show you a little bit of this. So I had mentioned before a little bit about getting access to information behind here. So this is actually a cluster of galaxies. Remember, each dot here, each galaxy represents 100 billion to 200 billion stars. So if we look at the particular galaxy I was pointing at, you can connect with an actual image of that galaxy. This is the spectra, and you can actually connect and download the data for that particular spectrum to look into that particular galaxy. So the data in terms of this particular galaxy, each of these, notice they are a different size, different shape, different colors. There's 1 million galaxies here from the Sloan Digital Sky Survey, and there are only 10,000 astronomers in the entire world. And there's no way all these astronomers can go and classify these. So there was a crowdsourced site called galaxyzoo.org where people were taught how to classify galaxies, and that metadata was incorporated in here. And that's why you're seeing this where each galaxy is reflected accurately. So Worldwide Telescope is a free tool. It's at worldwidetelescope.org. We've launched it two years ago at the TED conference, and it's used on every continent on Earth, including Antarctica. I think we've passed too many millions to count. Both the last presenter, one-on-one, and Worldwide Telescope were selected as Time Magazine's 50 best places on the internet. So I think my time is up, but come and see me, of course.